Okay, welcome back to Mr. Hassan's Maths channel. I'm answering a question from one of the C4 papers from June 2018. This is Edexcel, the old syllabus, and this is actually related very much to P4. You have part 1, A and B, which is all about partial fractions and then integration of that. Part 2 is what actually somebody has really requested me to answer, but I want to go through I'll just do the whole question just to be complete. And there's a few points that are important for us to understand from these questions. So first of all, we have this partial fraction, this fraction. We want to split it up into separate parts. They've given us the form in which we need to do so that's not a big deal. It's quite easy for us to deal with this. Sometimes they don't give you the form. They'll just say express this as partial fraction. So you have to know how to do that. Right? There are other videos I have which explain in some detail how to do that, but just as a quick summary, first thing you check to see, is it an improper fraction? It's an improper fraction if the numerator is of an order which is the same or greater than that of the denominator. Okay, the order of the numerator here is linear. The highest power of x is 1. In the denominator, the highest power would be x cubed. If you were to expand these brackets, you get x to the power of 3. There'll be a 4x squared here, and there'll be an x. 4x cubed would be the, so x cubed would be the highest power. Therefore, it is a proper fraction, so that's why we don't have like a quotient part and then your fractional sections. It just splits up into 3 factors. Now, one of the factors is a bit weird because it's a repeated repeated factor. Repeated factors split up in this particular way. You have a constant over the factor plus another constant over the factor squared. And then this is a normal factor, just a constant over that factor. These are always... We only deal with these linear type of factors. The only thing we have is sometimes a repeated linear factor like this. Okay, so that's, if they hadn't given us that, we should know how to, split it up in this form. Now, from what they have here given us, we can go ahead and find the values of A, B, and C quite easily. And the way we need to do that is to, first of all, let's get rid of the fractions from this identity by multiplying both sides by 2x plus 1 squared times x plus 3. So both of these I'm going to multiply by 2x plus 1 squared times x plus 3. So I'll multiply both sides of this by that. So if I multiply this side by that, basically they just cancel out. You're left with 13 minus 4x. That's our left side of the identity. And the right side of the identity is going to be made of 3 parts. I'm going to multiply this fraction by this term, in which case one of the 2x plus 1s cancels out, and you're left with 2x plus 1 times x plus 3 multiplied by your a. So you have 2x plus 1 times x plus 3. And when you multiply this by this term, the 2x plus 1 squared cancels out, so you're left with plus b times just x plus 3. And when you multiply c over x plus 3 by this term, the x plus 3s cancel out, leaving you just with 2x plus 1 all squared. Now this, we can find the value of A, B, and C in a variety of ways. Probably the easiest way to start is to find a value of x which makes these brackets 0, some of these brackets 0. So let's look at x plus 3 first. X plus 3, what makes it 0? Well, that's when x equals negative 3. So if I substitute x equals negative 3 wherever I see x, the brackets which have x plus 3 will become 0. This will be something times 0, this will be something times 0, and we will only left with the c as an unknown. So I'm going to put minus 3 wherever I see x. So I have 13 minus 4 times negative 3. And here this becomes 0, this becomes 0. I'm left with c times 2 times negative 3 plus 1. And that's going to be squared, right? So that's 13 minus 12, or plus 12, sorry, which is 25. And this is going to be minus 6 plus 1, which is minus 5. Minus 5 squared is plus 25. So you have 25 equals 25c. So therefore we can say c equals 1. So I know there's a 1 over there. Similarly, we can also think about what makes this other bracket 0, 2x plus 1. So what makes 2x plus 1 become 0? Well, that's when x equals negative a half. So if I substitute negative a half instead of x, then the brackets which have 2x plus 1 will become 0, and I'll be left with just this b bracket. So I'm going to put 13 minus 4 times negative a half equals, now this becomes 0, this becomes 0, I'm left with b times negative a half plus 3. So this becomes 13 plus 2, which is 15, equals and this is 3 minus half, which is 5 over 2. So this is 5 over 2 times b. So multiplied by 2 gives me 30, divided by 5, 6. So therefore b is equal to 6. So I found what b is and I found what c is. Now what's left to find is a. Now to find a, we cannot use this substitution method, because where a is, if I put x equals minus 3, this becomes 0. If I put x equals minus half, that becomes 0. There's nothing I can substitute which will eliminate these others and leave me with just a. So what I'm going to resort to now is what's called comparing coefficients. So I'm going to think about the coefficients of x squared of the terms on both sides. Now the highest possible coefficient of x, of the possible power of x, is x cubed in this case. All right. No, in fact, it's going to be x squared in this case, sorry. Because when I expand these brackets here, I'm going to get, that will be 2x squared, and that will be 4x squared, right? 2x all squared. Those are the highest possible values that you can get for the powers of x. And it's always best to choose the highest or the lowest. Could use a constant as well. All right. If you choose like x terms, it's going to be too many combinations, especially for this and that. So it makes it more complicated. So always choose the highest or the lowest. So on this side, we don't have any x squared terms. If I compare the x squareds, I have 0x squared on this term, on this side. Here I'm going to have 2ax squared. So that will be 2a. And this won't give me an x squared term, sorry, but this will give me 4cx squared, because this becomes 4x squared times c, so that'll be plus 4c. Now I know c already is 1, so I can say that 0 equals 2a plus 4, so 2a equals negative 4, so a is equal to therefore negative 2. So now I can write my fraction in the form required. So I have 13 minus 4x, 13 minus 4x divided by 2x plus 1 squared times x plus 3 gives us a, which is negative 2 over 2x plus 1, plus b, which is 6 over 2x plus 1 all squared, plus c, which is 1 over x plus 3. Okay, so we've got the values of a, b, and c, and we are ready now to move on to part b, which says hence, means use what we just found. Find the integral of 13 minus 4x over 2x plus 1 squared over x plus 3. So that's what we started with. So we can simply just go ahead and replace this with what we found. Now what I'm going to do is I'm going to write the 1 over x plus 3 first. I'll have minus 2 over 2x plus 1. It doesn't matter which way you do it. And I'm going to get this one ready to be integrated. This is 6 times 2x plus 1 to the power of minus 2. Now some people will say, how come you got this ready to be integrated by writing it in the numerator with a negative power, and you didn't do it for example, 1 over x plus 3. Now 1 over x plus 3 is going to be raised to the power of negative 1. Right? If I try to integrate this in the normal way, okay, I'll end up with 0 in my denominator. Okay. Now, there's a few points I want to also mention about this integration, because the question that the student was asking, who asked for, especially the next part of the question, kind of gives me an idea that they have some kind of misunderstandings on certain issues. All right. Now, so first of all, what I want you to understand is that when you have something which is a function, okay, multiplied by a function, something like this. Let me just write it out first. So you have here a function inside another function, multiplied by the differential of that function, of what's inside that other function. So this is a function inside another function, and the differential of this thing is multiplying that whole function. This is only when you can use the reverse of the chain rule. Okay, you can't use it otherwise, right? So in this case, I can use it because I have inside the function something. If I differentiate it, I'm going to get a constant. Outside the function, multiplying it is the differential of what's inside. It doesn't have to be exactly the same number, but it has to be the same order. It's an x. This is a constant term. This will be a constant term when I differentiate it. And that's fine. So this is of the form. I'm going to use the reverse of the chain rule to integrate this. These two, I'm going to use some form of the reverse of the chain rule, but it's not quite the same. Okay. In this case, when you have 1 over something, when you have a fraction, not even just 1 anything over something, it's like a fraction. If you notice that the numerator is of the form of the differential of what's in the denominator, then you can use the ln of whatever's in the denominator. You can use that to integrate. Okay. So, and the reason for that is, for example, if I have the ln of x and I differentiate it, I get 1 over x. Right? And if I have, for example, the ln of x squared and I differentiate it, I get 1 over x squared, then multiply by 2x. Notice what we have here. We have 2x. Let me put it as x squared plus 1 to make it a bit clearer. I end up with 2x again. Yeah, multiply by 2x. I end up with 2x over x squared plus 1. The numerator is of the form of the differential of the denominator. Okay, so when you see that form, you know we can integrate and it will become something like that, which we'll go into more detail in later. All right, so you can use the reverse of the chain rule either with ln or with the forms that I have mentioned. Okay, just now. So what we're going to do here is we're going to integrate this. So I'm going to take the integral of this. So I know that this is, the numerator is 1, the differential of x plus 3 is 1, a constant like 1. Therefore, I can use ln. So I'll say ln of the modulus of x plus 3. Always write the modulus because what's inside it can never be negative. That's like a simplistic way of explaining it, but that's all right for now. Minus, and here I'm going to have 2 times the ln of the modulus of 2x plus 1, but then divided by 2. Okay, why divided by 2? Because we're dividing by the differential of what's inside the function, and that will cancel with that. And here I can't use the ln thing. Supposing I wanted to use the ln thing for this, I can't, because if I differentiate 2x plus 1 squared, I don't get 6. I don't get a constant at all. So you can't use the ln thing. But what I can use is the reverse of the chain rule, in the fact that what's outside the function is a constant, and what's inside the function, if you differentiate it, becomes a constant, and the main function is something raised to the power of minus 2. So how do I integrate something raised to the power of minus 2? Well, if it's like this polynomial type, I add 1 to the power, and then divide by the new power, and also I divide by the differential of what's inside the function, which is that 2. So I end up with ln of the modulus of x plus 3 minus ln of the modulus, don't forget the plus c, by the way, ln of the modulus of 2x plus 1, and this is going to become minus 6 divided by 2 is 3 times, and I can put over. I can leave it like this if I want to. That's fine. I can leave it like this. 2x plus 1 to the power of minus 1. Or I can write this as 3 over 2x plus 1. That's fine. Okay, that will be my answer for this question. Right, so we have now integrated, and plus c, of course. We have now integrated this expression. We could combine these together as ln of x plus 3 over 2x plus 1, that's fine, we can do that. No need to, the question didn't tell us to put it in any particular form. This is fine as our answer, all right? Now, just as a little, indication, why could we integrate this to become that? Why could we add 1 to the power divided by the new power? Only because outside here was a differential of what's inside the function. If it wasn't the case, then we would not be able to do that. Okay, and we can check each of these answers. We can check to see, do we get those when I differentiate them? That's how you can always check. If I differentiate ln x plus 3, I get 1 over x plus 3. If I integrate ln of 2x plus 1, I get 1 over 2x plus 1, and then multiplied by the differential what's inside the function, which is 2. If I differentiate this, I'm going to multiply by the power, so I get plus, and I have 1 times 3, that's 3. And I have to do 2x plus 1, take 1 from the power, and then multiply by the differential of what's inside the function, which is 2. So I end up with 6 times 2x plus 1 to the power of minus 2. And this gives you 2 over 2x plus 1. And this gives you 1 over x plus 3. So this is like a little check. And of course, the plus c becomes 0. So we can see that we get exactly what we started with when we differentiate our answer. Okay, so that's one way to make sure that you haven't made a mistake. Now I'm going to go on to part 2 of this question, and it's really important, actually, next part, and that's where the student was asking questions about. Anyway, So that concludes this particular video. So this is the answer here. That part is a check here. That's the actual answer. So that concludes this part. We're going to go on to the next part now. Okay, now for question 3, part 2. Now this is where the student was having some problems. So the student was saying basically, why can't I do this? Why can't I do the following? Which was to write this as e to the power of x plus 1, add 1 to the power, divide by the new power, and divide by the differential of what's inside the function, which will be e to the power of x. Now you tell me what happens when you differentiate this and compare it to what we had over here. If I was to differentiate ln of x plus 3, what am I going to get? I'm going to get 1 over x plus 3, which is what we started with. Okay? If I was to differentiate this, I'll get 1/2 times 1 over 2x plus 1 multiplied by the differential of what's inside the function by the reverse, by the chain rule, multiplied by 2. That cancels with that, leaving you with exactly what we started with. Right? However, if I was to differentiate this, there's no way I'm going to get that. This I have to use the into differentiation. I have to use the quotient rule. I'm going to end up with some really, complicated, thing. I have to have u equals ex to the power plus 1, e to the power of x plus 1 to the power of 4, and v equals 4 e to the power of x, and I have to find u dash, and I have to find v dash, and then I have to do this times that minus that times that divided by this squared. There's no way I'm going to end up with this. Okay, so for sure this is not the result of the integral of this, and the reason why is because it's not of the form. We can't use the reverse of the chain rule because it's not of the form f dash of x times g of f of x. It's not of that form. Okay, outside this function is 1. And the differential of e to the power of x plus 1 is e to the power of x. If it was e to the power of x times e to the power of x plus 1 to the power of 3, yes, I could use that. If there was an e to the power of x there, I could use the reverse of the chain rule. If I wanted to integrate this, because outside of the function is the differential of what's inside the function. Even if it said 2 times e to the power of x or half of e to the power of x, as long as it says some multiple of e to the power of x, it would work. All right, so for example, let me start like this. Here, in this case, I recognize this form, so I say, okay, let me write it as the first part as it is, and this as it is, except I'm going to raise the power by 1. Why? Because the main function here is something raised to the power of 4. Divided by the new power, and then you multiply by the differential of what's inside the function, which is e to the power of x. Notice what happens. They cancel out. So you're left with a half e to the power of x plus 1 to the power of 4. Now, if I was to differentiate this to check, do I get that answer in the end? Well, I have to multiply by the power, so I have 4 times a half, which is 4 over 2, e to the power of x plus 1, take 1 from the power, and then because of the chain rule, multiply by the differential of what's inside the function, which is e to the power of x. So I'm left with 2 e to the power of x times ex plus 1 to the power of 3. We get exactly what we started with. So when you differentiate your answer, you know that you've done it correctly. If you try to do the same thing for this, as I showed you, there's no way that the answer you get, which will be e to the power of x plus 1, if you think that you could do this, this will no way give you this when you differentiate. No way, because you've got to use the quotient rule. Okay, so it's very, very important for you to understand that point. Okay, that's why we cannot use reverse of the chain rule. Okay, we cannot use reverse of the chain rule in this case. All right, that's one thing. Now, there might be a few other points where you have some confusion, but I'm going to go through it. So the only way really to integrate this is to expand the brackets. Okay, is to expand these brackets. Okay, so what I'm going to do is I'm going to just, we could do it by understanding of binomial expansion, but I'm just going to do it like the long way. So I'll just do it over here, ex plus 1 times ex plus 1 squared, right? Now, ex plus 1 squared is e to the power of x, and I'm going to write it like this for now, just so that you understand. It's like you square the first term, you multiply these two together, and double that, so it's 2 e to the power of x times 1, and then you square the last term, is going to be a 1, and when you expand this bracket, you have e to the power of x times e to the power of x squared, which will be e to the power of x cubed, plus, and you multiply this by this, that will be 2 e to the power of x, and that will be squared. And then e to the power of x times 1, which is e to the power of x. And then you've got to multiply by the 1 here, so that's 1 times e to the power of x squared. And 1 times 2e to the power of x, which is 2e to the power of x. And 1 times 1, which is 1. So we end up with e to the power of x all cubed. I'll write it here for now. Plus 3 e to the power of x squared plus 3 e to the power of x plus 1. Now, e to the power of x cubed, e to the power of x all cubed, remember you multiply the power. A to the power of m to the power of n gives you a to the power of m times n. So I multiply these powers, so that's going to be e to the power of 3x. X times 3 is 3x, right? So that's going to give me e to the power of 3x. And that will be plus 3 e to the power of 2x plus 3 e to the power of x and plus 1. So when you expand that, this is what you're going to get. And now we can integrate each of these terms. And now here's another point where I think maybe the student from the words of their comment is confused. They say, why can't we just add 1 to the power, okay, of this like you do when you have, for example, x cubed? That's going to, when you integrate it, you're going to get x to the power of 4, then divided by 4, right? Because not everything integrates in this way. Not everything integrates by adding 1 to the power and dividing by the new power. Okay, when you have sine of x, how does it integrate? Do you add 1 to the power divided by the new power? No. Sine of x becomes cosine of x when you differentiate it, and when you integrate minus cosine of x. If you integrate cosine of x, you're going to get sine x. You don't add any powers. When you integrate 1 over x, that becomes the ln of x. Ln of the modulus of x, in fact. All right? So different functions integrate in different ways. They don't all integrate in the same way. A to the power of x becomes a to the power of x over ln a. Okay? Very important for us to understand. Not everything integrates. If you have, some polynomial, x to the power of 3, for example, then you add 1 to the power and divide by the new power. Only that type. So in P1, in IGCSE or GCSE, P1 and P2, we only dealt with this type, where when we're differentiating and when we got to P1 and P2 integrating, we only dealt with this type where you have a polynomial type of problem. But these came in P3, all right? We got these in P3. So not everything integrates by adding 1 to the power and dividing by the new power. Not everything differentiates by multiplying by the power and taking 1 from the power. Not everything, only the polynomial, that's only one type of integration and one type of differentiation. Different types of functions integrate in different ways, so we have to know how they integrate. Now, e to the power of x, something's very special about this. This is called the exponential function. When you differentiate it, it doesn't change. When you integrate it, it doesn't change either. Okay, so this is an example of where we can integrate this using the reverse of the chain rule, because e to the power of 3x, here you have a function inside the function. Outside the function is 1. 1 times e to the power of 3x. If you differentiate what's inside the function, you get 3, which is constant, and this is multiplied by constant. So I can use the reverse of the chain rule for each of these, and this one just becomes x, of course, because it's a constant, right? So for each of these, I can use the reverse of the chain rule. I can say it integrates by doing what? By staying the same. E to the power of something integrates by doing what? By staying the same. But then, because there's a something inside the function, there's a function inside the function, which is 3x, I have to differentiate that and divide by that. That's going to be divided by 3. Differential of 3x is 3. Okay, and there's my answer. And if I want to check my answer is correct, I can differentiate this term. If I differentiate this term, what happens? Well, it stays the same. And then I have to multiply by the differential what's inside the function. So I'm starting off with 1/3 e to the power of 3x. If I differentiate that, it stays as 1/3 e to the power of 3x. Okay, but then I multiply by the differential of what's inside the function, which is 3. The 3's cancel, leaving me with what I started with. So you can check to see if you're correct, right? For each term. And then for the second term, same thing. You have plus. Now, this stays the same first. That's how you integrate them. E to the power of something just stays the same. Outside the function is the differential inside the function, so we're fine. Okay, this is a constant, that differentiates to become a constant. But then I have to divide by the differential of what's inside the function. The differential of 2x is 2, so I'm going to write 2 here. Similarly with this one, this is going to be 3 e to the power of x. Well, it just stays 3 e to the power of x. If I can say divide by the differential of what's inside here, which is going to be 1 anyway. And then 1 becomes x, and don't forget your plus c. This is an indefinite integral. Let's write plus 3. And there's the answer. That's it. Simple as that. We can, if you want to write it as a third, e to the power of 3x plus 3 over 2 e to the power of 2x plus 3 e to the power of x plus c, that's fine. Okay, so not everything integrates in this way. That's just one of them. Whoops, what happened there? That's just one type of integral. Okay, not everything integrates in this way. You have different ways that things integrate. So e to the power of x becomes itself. But then you have to use the reverse of the chain rule. If this was, for example, x e to the power of 3x, I couldn't use the reverse of the chain rule because it's not multiplied by the differential of what's inside the function. Okay, I can't do that because if I tried to do if I tried to do that, it would be x e to the power of 3x divided by 3. Well, if I try to differentiate this to see if it comes back to becoming that, well, it doesn't. All right, because what's going to happen is I'm going to have to use the product rule. It's going to come out something weird, things added together. So this won't work. Why? Because it's not multiplied by the differential of what's inside the function. If this was a 3x squared here, then it would work. It would work because it's multiplied by the differential of what's inside the function, or the same order. It's x, that's, if you differentiate, you get 6x. 6x is a multiple of x. So, for example, here what I would do is I would say, okay, this stays the same, but then I have to divide by the differential of what's inside the function, which is 6x. And you see what happens? The x cancels out. So you're left with 1 over 6 e to the power of 3x squared. And then if you differentiate this to see, do we get the same answer in the end? Well, if you differentiate 1 over 6 e to the power of 3x squared, if you differentiate that, you're going to have 1 over 6 e to the power of 3x squared. It stays the same, but then you multiply by the differential of what's inside the function, which is 6x. The 6 is cancelled out. You're left with x times e to the power of 3x squared, which is exactly what we started with, right? So that's why the rest of the chain rule works. Okay, and that's why we couldn't integrate this in the way that you were talking about, right? So there's the answer for question 3 part 2, which we were asked. That was what was being asked in the comments. But just to complete this question, I'm going to answer the next part of the question, which is 3 part 3, which is using substitution, u equals x cubed, u cubed equals x, or otherwise find the answer to this. Now I'm going to use this substitution that they asked us to use. That's probably the easiest way of dealing with it. Okay, so let's deal with that substitution. Now I know that when we do substitution, what I like to do is define y as everything that I'm integrating, which is 1 over 4x plus 5x to the power of a third. That is what I am integrating. And when I use substitution, our objective, remember, is to find what y is with respect to x. Here we don't have any limits, so our answer is going to have to be expressed in terms of x in the end. But in order for us to use substitution, I have to put y dx du. So initially I have to integrate everything in terms of u. So I have to change everything in terms of u. So if there were limits here, I would have to change the limits in terms of u as well. But as there are no limits, I don't have to worry about that. Okay, but basically the y and the dx du have to be expressed in terms of u. So you have u cubed equals x. So I can say x equals u cubed. So I can say dx du. If I differentiate this with respect to u, it's going to be 3x squared. 3u squared, sorry. 3u squared. And my y, okay, so I know that u cubed equals, x equals u cubed. So I'm going to replace the x here with u cubed, basically. Simple as that. So this is going to be 1 over, instead of x, I'm going to put u cubed. And instead of plus 5 times, now this will be u cubed to the power of a third, which is going to basically be u, right? And times dx du, which is 3u squared du. There's no limits here, so I don't have to worry about that. So this is going to give me the integral of, this will be 3u squared on the numerator over, and this is 4u squared plus 5u, because 3 times a third is 1, so it's going to be 5u to the power of 1. Okay, now I can see that there's a common factor, and that has to be integrated with respect to u. So now I can see that there's a common factor here of u. So I'll write this as the integral of 3u squared over, take out that u, I'll have 4u squared plus 5. That cancels with that. So I'm left with this, integrated with respect to u. So now I'm going to have 3u over 4u squared plus 5. Okay, 4u squared plus 5. And that's integrated with respect to u. Okay, so yep, we cancel out the common factor. Now, what I notice here is what I was mentioning earlier, that this is in the form f dash of x over f of x. That the numerator, if I differentiate the denominator, I get 8u, sorry. The numerator is 3u. That's some multiple of 8u. It's like the same order. So I can use the ln function here. So I can say that this is going to give me, and the way I like to do this, I'll write 3u times the ln of the modulus of 4u squared plus 5 divided by the differential of what's inside the function, which is 8u. You'll notice that the u's cancel out. I've got plus c here, right? So I've now got my the form of the answer. We have to do something in the end to give the actual answer here. But it's 3 over 8 ln of 4u squared plus 5 plus c. All right, and we can check to see, does this give us that if we differentiate it? So if I differentiate this just as a check to make sure, if you differentiate this, you have 3 over 8 times, now the ln of something becomes 1 over that thing, as it is, but then multiplied by the differential of what's inside the function, which is going to be 8u. So the 8 cancels with the 8, and you're left with 3u over 4u squared plus 5, which is exactly what we started with here before we started integrating. So we know that this definitely is the integral of what we had there. And now we have to express our answer in the end. We used u as a means of integrating. We don't have limits here, so we're not making a numerical value, but we're going to use the substitution and reverse it now. So u cubed equals x. We were told to use u cubed equals x. So wherever I see u, I have to replace it in terms of x. So that means u is equal to x to the power of a third. So I'm going to replace the u with x to the power of a third. So I have 3 over 8 times the ln of the modulus of 4 times, and this is going to be x to the power of a third raised to the power of 2 plus 5 plus c. So that gives you 2/3 as a power. You multiply the powers. So that gives us our final answer, 3 over 8 times ln of the modulus of 4x to the power of 2/3 plus 5 plus c. And there's the final answer of this question. And that concludes this particular question from the June 2018 C4 paper. Very important points in this video here, which hopefully has gone some way to kind of like clearing up some misconceptions that I think some of the students, or the student in particular who asked this question, had. All right, so other questions from this particular paper, when I get to answer them, will be in the playlist that should appear. The link for it will appear over here. Other questions from the topic of, well, I guess this is a lot of different types. Let's say integration in general. I'll put this under substitution, and I'll also put this under partial fractions as well. And you can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.